Hi everyone, welcome back. We are very pleased to have Ramon Aliaga from Valencia, and he's speaking on the Radon-Nikodym property and Schur properties in Lipschitz-free spaces. Ramon, please.
Okay, thank you. Also, thank you very much, Benjamin, for the organization, and of course, thank you everyone for being here. Okay, so what I will be showing you today is part of a joint work with Chris Garland, Colin Petitjean, and Tony Prohaska. And I will start by clarifying what I mean in the title. I guess this slide is not really necessary for this audience, but just in case, you know. Okay, so recall the definitions of these properties. So for a Banach space X, we say that it has the Schur property when weakly convergent sequences in X are also non-convergent. And we say that X has the Radon-Nikodym property, or RMP for short, if the original definition is that the Radon-Nikodym theorem holds for X-valued vector measures instead of standard real-valued measures, but there are many equivalent characterizations, and I guess one of the more manageable ones is this one. So it's RMP is the same as saying that every Lipschitz path into X is differentiable almost everywhere. And as you probably know, these properties pass to subspaces. They are invariant under isomorphisms, also undertaking countable L1 sums. And
Ramon, are you able to make it a little louder?
I guess so.
Okay, yeah. If you click on the microphone button, you can probably change the slider a little bit, the sensitivity.
Okay. Is it louder now?
Yeah, it's better. Yeah, thank you.
Okay, sorry about that.
Yeah, that's fine. Okay.
Okay, well, anyway, you already knew what I told, so that won't be a problem. I was just saying, yeah, both of these properties go to subspaces. Little L1 has both of them. In fact, little L1 is the prime example of a space with a Schur property, and capital L1 has neither of them. And in general, neither of these properties implies the other one, even for subspaces for capital L1, for instance. But I will show today that for Lipschitz-free spaces, they are actually equivalent properties. And Lipschitz-free spaces have already appeared in this webinar many times, but since it's the first time this year, I will get to introduce them yet again. So here we go. Our setting will be dealing with complete metric spaces M with metric D, where we fix some base point, which we call 0, and it doesn't really matter which point we choose. Then we will be considering real valued functions F on M, where the Lipschitz constant is defined as usual. It's just the supremum of these incremental quotients here. And what we call the Lipschitz space is the space of all Lipschitz functions that vanish at the base point. And the reason why we choose this extra condition is so that the Lipschitz constant is a norm instead of a semi-norm in this space. So it's a Banach space. We can consider the evaluation operators on points on M. These are obviously elements of the dual of the Lipschitz space. And in fact, these are isometric embedding of M into this dual. And if we consider the closed space generated by these evaluation operators, then this is what we call the Lipschitz-free space over M, or sometimes also called the Arendseel space. And this is a subspace of the dual, but it's actually also an isometric pre-dual of the Lipschitz space. And in fact, the weak star topology that it induces on the ball is just the topology of pointwise convergence. And just to take a brief look at how these spaces look like, let's look at two important examples. So first of all, if the metric space is just the natural numbers as a subspace of the real numbers, then the free space is just little L1. And this is the isometry that shows that. We just take any point n into the corresponding element of the summing basis of L1. And if our metric space is the unit interval, then the free space is capital L1. And the corresponding isometry is the continuous version of the same idea. Here we take a point X into the characteristic function of of an interval starting at 0. And well, this holds for the unit interval, but in fact, for the whole real line, we get the same thing with the same isometry. And the reason why usually Banach space people are interested in these spaces is because of this linearization property here, which is as follows: is if we have any Lipschitz mapping from a metric space into a Banach space, then we can extend this to a linear operator from the free space into the same Banach space. And here, this extension is meant in the sense that M is identified with its isometric copy in the free space, so such that this diagram here is commutative. And another way of saying this is that Lipschitz functions from the space of Lipschitz functions from M to X is the same as the space of operators from the free space to X. And when X is itself another free space, then what we get more generally is that any Lipschitz mapping between two metric spaces can be extended to an operator between the free spaces. And this, this linearization property is interesting in order to study nonlinear geometry, for instance, of Banach spaces. If M and N are chosen to be Banach spaces, then we get a linear operator between the corresponding free spaces whenever we have a Lipschitz mapping between them. And well, it follows from these two properties that when we have two by Lipschitz equivalent metric spaces, then their free spaces are isomorphic. If one space Lipschitz embeds into another one, then we have an isomorphic embedding of free spaces. And in fact, when this embedding is isometric, then it turns out that the free space over a subset is just a subspace of the free space over the whole space. And one non-trivial observation about this is that these subspaces of, Lipschitz free spaces over subsets are closed under intersections. And if we consider the intersection of the free spaces over some family of sets, then this is just the free space over the intersection of these sets. And based on that, we can define the support of an element of a free space like this. It's just the intersection of those sets such that our element mu belongs to the free space over that set. Well, in fact, we can make this definition regardless of the theorem above, but what this theorem tells us is that mu always belongs to the free space over its support. So the support is contained in this set here, and we can define it as the smallest closed set, such that this thing here holds. Okay, so much for the basic theory of Lipschitz-free spaces. Now I will speak about one specific type of Lipschitz functions, which we call locally flat. So we say that the function is locally flat at the point X if this condition here holds. So if we take neighborhoods of X smaller and smaller, and we consider the Lipschitz constant of F when restricted to this neighborhood, then this Lipschitz constant go to 0. So you can picture this as the F having a null derivative at this point, if you think, for instance, that our metric space is the unit interval or so. And we denote the space of locally flat Lipschitz functions like this. We usually call this the little Lipschitz space. And so, for example, when our metric space is the unit interval, then as I said, it's easy to picture that this condition means exactly that the derivative of F is 0 at every point. So the only little Lipschitz function that we get is 0. Okay, it's the constant, but since we're forcing a value of 0 at the base point, then we only have this trivial locally flat function. On the other hand, if our metric space is the natural numbers, this is a discrete space. So every F is locally constant and therefore also locally flat. So this is kind of the opposite situation where every Lipschitz function is little Lipschitz. And here's one more more interesting intermediate case. Suppose we have M to be a subset of the reals with measure 0. Then for every epsilon, we can cover M with an open set with measure less than epsilon. And then we can consider this function here, which is just, we integrate between 0 and x, a function which is 1 outside of U and 0 within U. Then this function is obviously locally constant of M on M, which is covered by U. So its restriction to M is also little Lipschitz. But in this case, the function has Lipschitz norm 1, and also it has this separation property here. So it maps 2 different points into values which are almost separated by their distance. So while not every function, not every Lipschitz function is locally flat in this case, they are kind of dense anyway. And this seems kind of disjoint from the rest of the talk. Like, why would I even talk about this? And we will see the reason now. Let's ask the following question. When is a free space a dual Banach space? So let's look for sufficient conditions for this. And one important sufficient condition for this when M is compact is that the space of little Lipschitz functions separates points uniformly. And this implies that the space of little Lipschitz functions is actually a pre-dual of the free space. And by separating points uniformly, I mean this condition here. So that for any 2 points in M and any epsilon, we can find a function of norm less than 1 such that this separation condition is satisfied. So this is exactly what I showed in the previous slide. So essentially what I proved in the previous slide is that when K is a subset of R with null measure, then this is satisfied and therefore its free space is a dual space. And some other cases where this is known to hold is when K is a compact holder space. So this is just any compact metric space where we take, we replace the metric D by the holder metric D to the power alpha, where alpha is strictly between 0 and 1. Also, this holds when K is a countable compact or an ultrametric compact or a 0 hyperbolic with measure 0. Or more generally, when its Hausdorff measure is 0. This covers all of these 3 previous cases, not the holder one. And the way why this is, the reason why this is true is very simple. Simply, if we fix any point in K and we consider the set of all possible distances to X, then this set is a subset of the reals with measure 0 because our space K has also Hausdorff measure 0. And then we know that for A, this condition is satisfied. So we take one function that satisfies this and we just compose it with the distance. And it's easy to see that then this function will satisfy the separation condition. So what we have is these implications here. The little Lipschitz space separating points uniformly is the same as it being a pre-dual of the free space, which implies that the free space is a dual. This is all for compact K, of course. And now we can find some more implications here. For instance, this implies that the free space has the RMP because then it's a separable dual space. It's also known that this condition here implies the Schur property. This was proved by Colin-Petitjean a few years ago. And in fact, not just for the compact case, for a general case, that whenever the little Lipschitz space is one norming, then we have the Schur property. We also have these implications here because little L1 has neither of these 2 properties. And now let's look at slightly more complicated condition here. We start by mentioning this theorem by Godard, who characterized the free spaces for any subspace of the reals. He proved that if M has measure 0, then its free space is just little L1. And if it has a positive measure, then its free space is one of these. So capital L1 plus some little L1 space of the appropriate dimension. Here, the dimension is just the number of gaps in M. In any case, f of M is isomorphic to capital L1. Now, there is one concept from metric geometry, which is that of curve fragments. These are by Lipschitz images of compact subsets of the real line with positive measure. So what Godard's theorem tells us is that the free space over any curve fragment is isomorphic to capital L1. And so if M contains some curve fragment, then its free space also contains capital L1. And another more interesting concept from metric geometry is that of purely unrectifiable spaces. These are spaces such that if they contain some Lipschitz image of a subset of the reals, then this image has to have Hausdorff measure 0. And it can be proved that this condition is equivalent to containing no curve fragment, so which is basically the same condition, but by replacing Lipschitz with bi-Lipschitz. And from this, it follows that this implication here, basically, if our free space doesn't contain capital L1, then it must be purely one unrectifiable, because otherwise it contains a curve fragment and therefore its free space would contain capital L1. So, well, we have plenty of conditions here, and our first main result that I want to show is that we also have this implication here, which closes the loop here. So whenever a compact is purely one unrectifiable, then its little Lipschitz space separates points uniformly, and therefore the free space is a dual. And this, now we will spend some 10-15 minutes detailing the reason why this is true. So yeah, let's try to prove this theorem. What we will do is we fix some point in K with some epsilon, and then to prove this, we need to construct a locally flat one Lipschitz function, which satisfies this inequality here. In fact, it's enough that we build such a G for any two pairs of points, but here we can fix one point and build this G that works for every X anyway, so we will do that. We will consider K to be contained in some compact convex subset of some free space. We can, for instance, just take the closed convex hull of K within its free space. And we will also assume that the diameter of K is 1, just because the formulas are much simpler that way. So this will be the form of the function that we will build. What we do is we fix some Borel function f, which is positive and bounded by 1, and then G will be the infimum of the integrals of f along all possible Lipschitz curves that start at P and end at X. So first of all, G of P is 0, of course, because then we just take the curve that goes from P to P instantaneously. And for every other point X, we have this bound here for the incremental quotients. This bound here follows simply from the fact that whenever we have a curve from P to X, then we can extend it by a linear segment, and we get a curve from P to Y. And in this extension, we have this integral on this extra segment, and then this will be bounded by the distance times the maximum of f in this segment. So this is where this inequality comes from. So it follows from here that G has to be one Lipschitz, but also if we choose the function in such a way that it goes to 0 as we go closer and closer to K, then this will also be one Lipschitz. Sorry, this will be locally flat when we restrict our function to K, which is what we want. So it's enough that we choose F to satisfy this, besides this inequality here. So we will build F like this. We will choose decreasing neighborhoods of K, which look like that. So we build a decreasing sequence of numbers Rn, and then if a point is in the nth neighborhood of K but not in the next one, then we assign it the value 1 over n. We will use a slightly different notation like this. We will use this notation, the bracket notation for the set of points that's a distance at most R from K. So then, yeah, if we're in the nth neighborhood but not in the nth plus 1, we assign it the value 1 over n. Then if we split this integral among all of these possible subsets here, well, I will be faster, a bit fast here, but we can easily get this inequality here for any natural number m simply by cutting this sum at the mth term. we get that this integral is at least the length of the curve divided by m minus the length of the part of the curve that lies within the neighborhood number m plus 1. And this is true for every m. And we can now choose one particular value of m, and we distinguish two cases. So if the length of the curve is at least 1, then we take the largest integer, be smaller or equal to this length. Then this fraction here is at least 1, which is bigger or equal than the distance between these 2 points, because we are assuming that the diameter of k is 1. And in the other case, then we just take m equals 1. Then this fraction here is exactly the length, which is also larger or equal than the distance, because gamma is a curve from P to X. So of course, its length is at least the distance between these 2 points. So this part here is at least the distance. And then if we want this to be true, we just need to check that this thing here is less than epsilon. So this is the condition that we need to satisfy. We have to choose the numbers Rn in such a way that whenever a curve has length at most n, then the part of the curve inside the nth neighborhood is at most epsilon. And we won't be able to get this exactly, but we are able to get something very similar, replacing the length here by the Hausdorff content. And here, let me remind you the definition of Hausdorff content. It's like that. So for a given set A, we consider countable unions of this set and the sum of the diameters of the covering sets. And well, the smallest of these possible values is the Hausdorff content. And here, this is very similar to the definition of the Hausdorff measure. In fact, the Hausdorff measure is the same thing, but we also add restrictions on the smallest possible size. No, sorry, on the largest possible size of these sets En. So this is smaller than the Hausdorff measure. Okay, so let's prove this lemma, which says that whenever for every maximum length L, we can find a neighborhood of K such that if a curve has at most this length, then this Hausdorff content is bounded by epsilon. And the way to prove this is by contradiction. We suppose this wasn't true, which means that we can choose smaller and smaller neighborhoods here and a sequence of curves, gamma n, one Lipschitz curves, such that this is always at least epsilon. Let's also denote the pre-image of this part of the curve by an. Then we can pass to a subsequence such that these curves converge uniformly. This is just the Arcela-Ascoli theorem. We can also choose a subsequence such that these sets converge in the Hausdorff metric because the Hausdorff metric in the hyperspace of this compact interval is also a compact. Combining these two, we get that the corresponding images also converge in the Hausdorff metric. Here, the convergence is in the hyperspace of omega. And in fact, we have something more here because these images here are contained in smaller and smaller neighborhoods of K. So as we pass to the limit, we get that the limit is actually contained in K. And finally, we apply the fact that the Hausdorff content is upper semi-continuous with respect to the Hausdorff metric, which means that in the limit, this set here also has content at least epsilon, and therefore its Hausdorff measure is positive. And this here is exactly negating the fact that K is purely one unrectifiable, which is our only assumption for this theorem, because this is exactly the opposite of the definition of pure unrectifiability. This is quite technical, but I really wanted to show it because it's the only place where we are really using this hypothesis. Okay, so once we have this, we can choose numbers Rn such that this first condition is satisfied. And remember that what we need is the second one, which is the same, but using the length here. And while we cannot get this exactly, what we can do is we can build a perturbation of any curve gamma such that this is satisfied. And let me show how this perturbation is built. So let's say this is our curve gamma. let's say we have some ball here, then the operation we perform is we consider the first point where we cut the ball and the last point where we cut the ball, and then we erase the curve in between and we replace it by a straight segment. And then our resulting curve, its length inside the ball is at most the diameter, of course, because it's just a straight segment, and we are not increasing the length of the curve or its integral by more than this diameter. And now if what we have isn't a ball, but rather a neighborhood of K, then we cover the intersection with the curve by finitely many balls, such that the diameter is at most epsilon. This is the definition of Hausdorff content. Well, in fact, if within the definition, we use countable unions, but since we're dealing with compacts, we can just take finite unions, so we can do that. And then we apply this perturbation for a ball in each of these balls in turn. And this is the perturbation that we get. And so we get this condition here, which is what we wanted finally, and we are increasing the length and the integral, but no more than epsilon. And this means that we are already done, because then our function g, we can approximate it by integrating against some curve. Then we can approximate this curve by this perturbation here, and this satisfies our condition. So this is almost the same as the distance, or it's bounded below, but almost the distance. So this would finish the proof. There's just one small detail that can mess up this proof, and it's the fact that here we are increasing the length by a bit. So maybe this is true, that this is less than n, but then this isn't less than n because we have crossed the threshold of n. But if that's the case, then we just need to apply this perturbation again, because the second time we won't cross an integer threshold again as long as epsilon is less than 1/2. Okay, so this was a bit technical, but now we have this implication here. We have a closed loop of implications, and this brings us to this, which is our first main theorem in the compact case, that all of these conditions are identical. And let me highlight just a couple of implications here. So first of all, this gives a characterization of compact space H whose free spaces are duals, which wasn't known until now. And another one is that this shows that whenever the free space has a pre-dual, then one of the pre-duals is the little Lipschitz space. It's not a unique pre-dual because, for instance, the free space can be little L1, which has many non-isomorphic pre-duals, but we can be sure that this one is always one of the pre-duals. Okay, so well, this covers the compact case, and now let's see what part of this theorem we can carry over to the general non-compact case. So since we're dealing with the Schur property, we will be taking a look now at weakly null sequences or weakly convergent sequences in the general case. Here we have to recall Carlton's lemma from 15 years ago, who proved that whenever we have a weakly null sequence in a free space, then this holds. So for every epsilon, then for every r, we can find a finite union of balls of radius r such that we can find approximations of these elements of the weakly null sequence between the free space over such a set, which is also the free space over let's say, small subset of M. And in fact, this condition here, which we call K for Carlton, this condition holds for much more general spaces than, subsets than just weakly null sequences. This holds for every weakly precompact subset of a free space. And here, weakly precompact means that it's a bounded set and contains no equivalent L1 basis. For instance, weakly null sequences, of course, satisfy this. Okay, then we were able to prove last year that this condition K is in fact equivalent to stronger conditions, which we detail here. The first one we call T for tightness, because it's similar to tightness in measure theory, which says that we can replace this finite union of balls with a compact set K. Of course, this condition implies this one because we can always cover K with finitely many balls of given radius. And this last condition here is the same as this, but we are also saying that the approximations we can choose them such that the relationship is linear. So this is a linear selection of approximants within the free space of K. And in fact, there is a sequence of operators such that they converge pointwise, well, uniformly, in fact, for this set W. This doesn't converge to an operator on the whole free space, but just on this particular set W. And again, I will briefly sketch how we prove these implications and how we construct this compact set K. And we construct it iteratively. And in each step, we choose a finite union of balls of a radius which is converging to 0. And we just take the intersection of all of these. And these operators that we build, we always build them in such a way that they respect supports. So the support of the image of some element is contained in the support of the original one, and also in our set Kn, which is the intersection of the n first subsets like this. And the corresponding images form Cauchy sequences. The limit will be the approximation that we are looking for. And the reason how we are able to build this is that whenever we respect supports like that, then the corresponding image of W also satisfies a condition K. This is easy to see, which allows us to choose this particular finite set that we are looking for. Then we build this extra operator as a multiplication operator. I won't lose a lot of time with that. Just mention that we can choose this constant here correctly in such a way that this condition 3 is satisfied. So when we're done, we get our sequence of spaces Kn and our sequence of approximations here. This is always a Cauchy sequence. Its limit is at a distance epsilon from W. And this limit is contained, well, the support of these images is contained in every set Kn. So the support of the limit is contained in the intersection of all these sets Kn. And this is the compact we are looking for because by definition, this intersection is totally bounded. It is contained in finite unions of balls of arbitrarily small radius. So it's a compact set. And I have tried to make this very quick. I just wanted you to see the general idea, which is taking this intersection of finite unions of balls. And this is very natural. And one would think that Carlton would have been able to do that himself in his time when we proved this lemma. And I guess the reason why he didn't do this is because he, besides his lemma, he also needed this thing here, which is the intersection property that I mentioned at the beginning. This wasn't known back then, and it's a non-trivial fact that we need here in order to make sure that we can say this thing, that we can say that the limit is contained in the free space over K. Okay, so once we have this, now it's easy to prove this theorem here that says that a free space has the Schur property if and only if the free space over every compact subset of M also has the Schur property. So we say simply that the Schur property is compactly determined for free spaces. And one implication is clear, of course, by passing to subspaces. And for the other one, if we have a weakly null set in the free space, then by Carlton's lemma, it satisfies condition K. So it also satisfies the stronger conditions, which basically says that we have an approximating sequence Bn in the free space over some compact set. And now, again, I will skip the details, but you can check that then this approximating sequence here has to be weakly null, but it lies within the free space over K, which is Schur by assumption. So it's norm null, and then the same thing, but backwards, yet yields that the original sequence also has to converge to 0 in norm. So this proves, remember that we have already characterized when a compact is such that its free space has the Schur property. So this would already yield a characterization of the same thing in the non-compact case. And for the Radon-Nikodym property, which is the other one mentioned in the title of the talk, we can do something similar. Here, we need to use the martingale characterization of the Radon-Nikodym property. So whenever we have a probability measure space like this, we say that a Banach space has the, a Banach space X has the Radon-Nikodym property if this holds, if every uniformly integrable X-valued martingale converges in the corresponding L1 space. In fact, this has to hold for every possible probability measure space. I think that it's in fact enough is if it holds for the measure space given by the unit interval with the Lebesgue measure. So correct me later if I'm wrong. But I will just not write this thing for simplicity. Okay, then we can do a similar treatment like in the case of the Schur property. A probabilistic version of Carlton's lemma states that every martingale satisfies this condition here, which is sort of a mean Carlton condition. It's exactly the same, but here we are replacing the free space over this subset of M with the L1 space over this free space. So this would be measurable functions on omega that take values in not in the whole free space, but rather in the free space over this subset here. Then we can also prove an analog of this equivalence proposition that I showed you before. It's again exactly the same, but replacing free spaces with L1 over these free spaces. And the argument is almost verbatim the same. We just need to adapt the setting. And then again, using a similar argument, we get finally that the Radon-Nikodym property is also compactly determined. It's also given by the Radon-Nikodym property over compact subsets. And now that we have this, we can put all of this together in a big picture. So the Schur property for free spaces is the same as every compact subset satisfying it. Same thing for the Radon-Nikodym property. We already showed that this is equivalent. In fact, it's equivalent to a K, every K compact K subset of M being purely one unrectifiable. But pure unrectifiability is also compactly determined. So of course, because it's given by containing or not containing curve fragments, which are compact sets. So this is also equivalent to pure unrectifiability. And there's one more thing we can add here, which is not containing capital L1. We already included these arrows in the previous slide, but this actually doesn't depend on M being a compact. This holds in general, so we can also add this here. And now again, we have closed loops of implications. So this is really our main result, which is that all of this is equivalent. So for free spaces, the RMP and the Schur property are equivalent. They're also equivalent to not containing L1. And this holds exactly when M is purely unrectifiable. And as an easy corollary of this, we also get some other properties here for free, which are properties that usually lie between the RMP or the Schur property and not containing capital L1. Probably the most important of these is the Krein-Milman property. Remember that we say that X has the Krein-Milman property whenever every closed bounded and convex set is the closed convex hull of its extreme points. And it's known that that the RMP implies the Krein-Milman property, and this is obviously hereditary, and L1 doesn't have it. So since this condition here and this condition here are equivalent in our case, then it follows that the Krein-Milman property is also equivalent. And I guess you probably know that, but let me mention anyway. It's a famous and notorious open problem whether the Radon-Nikodym property and the Krein-Milman property are equivalent in general. This is not known. No counterexample is known. And this shows that we have no hope of finding such a counterexample within free spaces. Okay, there are actually some more properties that we can add here. They are probably not so important as the KMP. So one of them would be the point of continuity property. We say that a Banach space has this property whenever we have a closed-banded subset of X, it contains some point where the relative weak and norm topologies are the same. And again, this property is sandwiched between the Radon-Nikodym property and not containing capital L1, so it's also equivalent. And for the Schur property, we also have similar things. For instance, we have the uniform Kadetsky property. This says that for every epsilon, if we have an epsilon separated sequence in the ball, and this sequence converges weakly, then the limit has to be uniformly separated from the unit sphere. And this also lies between the Schur property and not containing L1. So again, this is equivalent. And we can probably find some other properties here. We haven't thought of much more than this, but there are surely some minor properties that we can include in this list here. I also wanted to highlight two things about that. One of them is that even though we can prove that the Schur property and the Radon-Nikodym property are equivalent, we are not really able to get any of the implications between them, because if you remember here from this slide, we are just proving their equivalence through the fact that they are equivalent for compact subsets. And in the compact case, we also have no direct arrow between them. We are proving that they are equivalent to not containing L1, but it's an individual separate proof for each of these conditions. So we are not really able to prove any of the implications directly. I think that's a remarkable thing from this proof. And so to close the talk, I see this has been shorter than I expected, but anyway, I don't have more slides, so I have to finish now. Let me just mention one more property that's not included in this list, and that's the fact that the free space is a dual space. We have seen that in the compact case, we have to add it here, but in the not compact case, that's not true. For instance, a few years ago, Luis Carlos García-Lirola, Colin Petitjean, Tony Prochazka, and Abraham Rueda constructed a countable uniformly discrete space M, which is therefore obviously purely one unrectifiable, but its free space wasn't a dual space. So this shows that this implication is not true in general. But let me also mention that the reverse implication is open as far as I know. So if free space is a dual space, must M be purely one unrectifiable, or equivalently, must the free space have the Radon-Nikodym property? If M is separable, then the free space is separable. So then the answer is yes, of course, because then the free space is a separable dual. But for non-separable M, this is not known. And I would expect that to be true. And I guess it won't be too difficult to prove really, but it's an open problem as far as I know. And so, okay, this is the end of the talk. Thank you for your attention. And let me just mention that the main reference, well, we have a list of references here, but the main reference, which is this one, isn't written yet. We are preparing the preprint with all of these results right now, and I hope it will be out soon, but it's not yet. So feel free to contact us for details or comments or whatever. Okay, so thank you very much.
Thank you so much, Ramon. Is there any question? You can jump in.
There are many natural questions. I think that's, sorry, it's a very interesting direction, of course. Let me ask the following, maybe you have an answer already. If you take, say, K, take the compact case to begin with, which is purely one unrectifiable, so you with all your equivalent properties, do you know if the free space over K has the approximation property, which would be equivalent with the metric version because of duality?
We don't know, and I can tell you we have been spending some time trying to prove that, because we conjectured that this is true. So yeah, it would have the MAP even, but we don't know. We have tried and we have failed so far.
Okay, well, parallel question to this. is to go to the pre-dual somehow. That is, I don't have an example, but maybe you know already, of a space of flat Lipschitz functions on any metric space that would fail, say, the bounded approximation property. Would you know of such an example, even if you leave the frame where you have a good separation as you did and so on? Just one space of little Lipschitz function, as sometimes we say, which failed the BAP. Would you have this in your drawer?
No, I haven't even thought about such a question. So I don't know. I will just mention that once you leave the compact setting, you have to be careful with exactly which definition of little Lipschitz you're using, because there are conflicted definitions, as you probably know. But the truth is, I don't know the answer for any of the usual definitions.
Okay, one last question, if I may, question or comment. I believe that at least in the case of your unrectifiable compact sets, the pre-dual of the free space is probably an M-ideal in the dual of the free space, right?
Mm-hmm. We haven't checked, and I know you have some results about this, but I don't remember all of them by now. I don't remember if it's always the case.
True. I mean, there are old things also by Yoav Benyamini in this direction, very old results. But then it follows, this is just a gadget, but I mentioned it in passing. It would follow that the little Lipschitz space is never unique isometric pre-dual. Okay, you gave the example of little one, but I believe this would be a bonus if you have this M-ideal business. It would forbid uniqueness of the pre-dual. Okay, this should be very easy to check. I mean, it's a 5 minutes business.
Yeah, we haven't checked, but as you say, it should be easy to check. So thank you very much for the suggestion.
Thank you, Ramon. Sorry for having been so long.
No problem. Any others? All right. If not, yeah, go ahead, please.
Sorry, I have one. Thank you, first of all, for the very nice talk and nice results. I was just somehow confused. If you could clarify, you had some isomorphic properties like Radon-Nikodym property, Schur property, and so on. And then there was the result concerning being a dual space. So this is isometric result, right? So
yes.
Yes,
okay. but it turns out that it's isomorphic. Well, I guess. Yeah, well, it's isomorphic. Pure unrectifiability is preserved by Lipschitz mapping. So in this sense, it's isomorphic. Yeah.
But the pre-dual is isometric, right?
Yes, it's yeah. I mean, when I say being a dual, I mean being isometrically a dual space. Yeah.
Mm-hmm. Okay, and in the case where the free space is a dual space, you don't have a candidate for the pre-dual. In the general case, I mean, not for in the compact case.
No, but there is a related thing. Like up till now, it was conjectured that in the compact case, the pre-dual would always be the little Lipschitz space, because for every known example, it always appeared that this was a pre-dual. And what is known for the general case is that, at least as far as I know, whenever there is a pre-dual, the pre-dual is a subset of the little Lipschitz space. Not the whole space, but a subset. So this would be my conjecture, that whenever there is a pre-dual, then there is one that is a subset of the little Lipschitz space. But this is open as far as I know.
Okay, thank you.
If I may, just to Marek's remark, this is a curious feature that in a compact case, whatever equivalent metric you put on a purely one unrectifiable metric compact, really its free space is going to be isometrically a dual. So in this sense, it is not surprising that you have on one hand side isometric result, and on the other hand side isomorphic one. This is how
Okay, thank you.
Okay, then thank you so much. If there is no others, thanks again, Ramon, for a very nice talk.